It's my great pleasure to welcome you to the 2020 Ben Tasker Memorial Lecture. We have the great pleasure of bringing Fernando Pereira here. Fernando is VP and Engineering Fellow at Google Research. He heads research in natural language understanding and machine learning, and came from a wide background of experience in both industry research and academic pursuits. He is fellow of the AAAI, ACL, ACM, and most recently the American Philosophical Society. And to me personally, and speaking to him both about research and other interests, it's always struck me so amazing how broad and deep his learning and understanding of different problems are. Specifically when we talk about the pipeline of translating research into real world applications, Fernando's knowledge and depth of knowledge is just so deep and almost alarmingly to the point where I come to the end of my depth and he's still working through some of these problems that occur in real life applications. And so it is with great pleasure that I welcome Fernando Pereira here for us today. Thank you.
Thank you, Annette. Thank you very much for inviting me. It's a great honor to be here. I mean, if I can start with a few words to why, when I was invited, I had to do this. I was a good friend of Ben's. I hired him to Penn, and I loved every minute I spent with him. And when I went to Google, which was a disappointment for him, I must say, I would come back and start talking to him about what I was experiencing and the work I was doing and the problems we're facing. And our conversations were always so inspiring. You know, he always had such a interesting way to think about the problems I was posing to him. You know, I remember, for instance, some question I was talking to him about with respect to news and how you present news in a diverse way. And that led to some beautiful work that he did with some of his students then on diversification in news presentation. And in fact, a lot of the discussions I had with him around diversity in news and in search results were very inspired by the work that he was doing with his students on determinable point processes, which, by the way, we use at Google for diversifying certain kinds of results. In fact, thanks to the work of his former student, Jenny Gillenwater, who's at Google now. So when I started thinking about putting together this talk, I started thinking about what kinds of things I would like to tell him, the kinds of things that he would be able to inspire me, to educate me, to tell me that I'm wrong, and so that's what I'm going to do here. I'm speaking here on behalf of a lot of people, and given my role today, I don't do a lot of direct research myself. I mean, I have a few things going, but mostly I work with others and try to make others do the best work they can. Help them find the resources, nudge people in directions that might be good. So some names, you know, many from Google, others are collaborators we've had in academia. You know, quite a few are former students of this wonderful institution. And I love working. Every one of you who wants to come and join us, I'm very excited to hear about that. But of course, you know, the best is when you all go over the world and not make just Google, but every place you go a better place. So this is a joke, sort of. One of my colleagues at Google runs the question answering product within search, and knows that John Blitzer, who was a former student of mine at Penn, he's at Google, works in that product as well, and said recently they launched an improvement in search in the question answering component using this deep models, BERT type deep models, and finally got this right. this is before it got something completely random, and now it actually gets the result that is appropriate, which is from John's own page. So I could say, hey, I'm done, we're done. No. But things are a bit more complicated. So this is a query. And now, by the way, all the examples I show from Google Search as a caveat. Between when I took the screenshots and now, the GNOME sitting in Mountain View might have changed things for the better, hopefully for the better. So if you go and try these examples and later and they don't work quite as I present them, sorry, we always try to make things better. So anyway, I don't know anything about this particular topic. Harry Potter is not my favorite literature, but it is of some of my colleagues, and so this is an example. And the interesting example is that it is the right answer, but if you look at the passage that selected that, it doesn't say anything about the order in which these particular characters played that role in the novel. So that's kind of a problem, right? We are presenting results to users, saying, hey, here's the answer to your question, but you're not giving them any reason for them to trust us. And this is going to be a big theme of my work today, my presentation today, is all these wonderful things we're doing in machine learning today have this great, they improve the quality of the, say, search results we get and the other things we do, but they suffer from an opacity of inability to inspire trust that we should be concerned with. So actually, there's another passage somewhere else in Wikipedia that tells you the story and tells you, in fact, this particular individual, I don't know even I'll pronounce that, is a successor of Snape and everything works. But this kind of situation should give us some pause. We have this so we're using fairly elaborate deep learning models to do search ranking and do question answering. And we're getting better results. We can measure on, human evaluators can see these results are better than that. And that's why these things have been launched. And yet we don't have a very good story of why things are the way they are. So thinking about this, I decided to kind of go back to my dark past. Some of you, most of you, hopefully, don't know this dark past because you've been trained in more enlightened times. But some of us had to suffer through logic. So I don't know who among you is a fan of Crazy Cat. This is a comic book from the 30s that Harriman created, and it's kind of very interesting and philosophical comic strip. I'm a great fan, and somehow, for reasons I can't even understand, I decided to use this as an example. So the cat is crazy, the mouse is Ignatz, and the mouse expresses its love, or their love, for the cat by breaking the cat. So people that, like me, that were trying to do language understanding back then would say, well, we're trying to describe, that scene. We might try to present it in the form of some natural language description, and the structure of the natural language description might somehow should be somewhat connected to the scene. How do we analyze natural language? Well, there's this thing called syntax that linguists have been developing for decades. And they know that there are the noun phrases and verb phrases, they connect in certain ways. And then you say, well, that is not quite directly as direct as connect to the image, so maybe we need a structure that is a little bit more abstract. And to say, well, there's something like brick here in the used as a verb for meaning throwing a brick at, or knocking the noggin with a brick or whatever. And there's a subject, which is Ignatz in this case, the bricker, and an object, which is crazy, the bricky. So we can look at this descriptively and say, yeah, there's a reasonable way of describing what's going on, but how do we connect all these things together? So you're looking at that structure, the kind of conceptual structure there, and I and some colleagues who were then at the Xerox PARC said, we need to be sure that when we're doing a mapping between this and some representation that we might be able to use for inference, for example, that we make sure that we account properly for each piece of that structure. That is, we don't forget anything, and then we don't overuse anything. Like if there's only one bricking going on here, not 17. So I should be able to manage that. And through a process that I won't go into, we use a certain logical formalism. For those who are interested, is linear logic, which I won't go into at all. And to manage, essentially, to do the bookkeeping of saying, well, I see Ignatz then produces some kind of representation of this mouse, and I see crazy, and it produces in my mind some representation that this of this cat, and then I see brick, and I produce it somehow in my mind a representation. If I'm given a bricker and bricky, and I put them together, I produce a representation of the event, and just did some kind of logical jiggery-pokery, which is basically keeping track of these premises and producing this conclusion. And I get my result, which is some kind of mental representation of the actual event. So this is the way we thought about things back then. I mean, we thought, oh, this is not a bad way to think. Because we keep track of information in a robust way. But the problem is whether that stuff all comes from. That people that are playing active roles in research in AI and natural language understanding today, that that's a very nice story, except that none of that comes from anywhere except the mind of the analyst. And if you want to actually build systems, you need to find ways of getting it from directly from the data that you observe. So through a long story of convolution of steps, what ended up happening roughly up to 10 years ago is people say, well, we want to do that thing, but we shouldn't do it by having people write rules and grammars and dictionary entries, but we should have them by doing machine learning on text, and maybe annotated text that linguists we hired will have annotated with different kinds of representations of the grammatical structure and the meaning and so on. And so the kinds of systems we're building back then were systems that might produce some kind of grammatical representation of the sentence, and then of the text, and then start identifying particular entities in the text and co-reference. Like, for instance, Harry Wessner in this passage is his refers to him, and so on and so forth. These things are all annotated appropriately with the appropriate types representing the kinds of things they are, like whether they're people or places and so on. And then you might extract some information from the whole thing and some assertions that there's some guy, Eric Wessner, there's some parents of his, they seem to have been from Poland, and he seems to be from North Carolina. And this kind of treatment of text and the kind of things we could produce, much of these steps could be done through some form of machine learning, although we needed a bunch of labeled data for it. And then if you wanted to do more complex things like doing inference with the results, you say, well, I really, really, really need is not just this this representation. I need to find some other representation kind of at the bottom here, that allows me to do inference. So for instance, in this case, that who did the acquisition, maybe Disney did, and who was acquired, what was acquired, maybe Pixar was. And we can learn the stuff up there from labeled data, although it's kind of a pain to get the data labeled. But what we do with these symbols at the end, you build these representations, and what are we going to do with them? And this is actually really a bottleneck for a lot of the work that some of us, including us, some of us at Google, and some of you I see in the audience, encountered, I would say, 7 years ago, 8 years ago, which was you produce these symbolic representations that are very good at managing the information in terms of making sure that all the pieces are there and only the right pieces are there. But it's really hard to do anything with them. So people tried. So some of my colleagues, working with the collaborators at the University of Edinburgh, came up with the idea was, well, I can take some expression like that. I can try to get a bunch of examples of how that expression relates to some representation, say, in a knowledge base, and do some form of alignment, say, oh, Pixar, oh, I can align these, and acquire, I can align that to the acquisition node, and could do this sort of alignments and combinations, and be able to produce systems that can relate the logical representations to some computational object, in this case a knowledge base, that you can do inferences with and can answer questions and so on. And basically, I think this is a high water mark of this kind of work, right? But, I mean, you can dispute that at the question period later, but my reaction is I was very big supporter of this work and very, very optimistic about it until I started seeing that people were working very hard and getting very little overall value out of it. In that the trade-off between, you could do this bookkeeping very well, but then you also, in many cases, you miss things because you didn't have the right alignments between whatever the symbolic representation was and the information that you have available to you, whether in some knowledge base, which is some graph representation or some logical representation or whatever other kind of representation you get. Explicitly, it was a very brittle and very unsatisfying way of processing language and trying to understand it and answer questions. And the practical reality is that all of this effort that we did over the, so I've been at Google since 2008. From basically 2008 to 2017, where I did a lot of this work, we did have some impact in different kinds of products through applying some of these techniques. But the impact we had was sort of like disappointing relative to the amount of effort we had put into it. I mean, we're paying our way, let's put it that way, but typically in ways that were kind of derivative relative to the main questions we're asking. That is, you could, it's one thing that I've, comment on my experience of being in these different worlds is that one of the things I've observed many times is that in many situations, the value of a researcher to an industrial organization is not the work they're doing now. It's the work they did 10 years ago. And, or even further. I mean, for me, my most favorite example is that I had been very interested in various kind of models of finite state machines very early on in my career. And it turned out that they come out to be very useful in doing speech recognition work at AT&T that actually led to some technologies that are still in use today. But, it wasn't anything I was doing then. It's stuff I knew from some books that were in my bookshelf, and I could say, oh, we should take that and turn it into code. So that's a little bit sad, right? You're doing all this research, but the way you justify it to the big boss is, hey, wait 10 years and it will be good for you. Or is the only way you keep me here is that if you allow me to do this crazy stuff. I think this is actually true of a lot of AI research in industry and even the relationship between academic AI research and funders. And this was sort of this slightly disappointing, yet even though we're doing kind of work that we thought and I still think is quite good. So these hidden symbols are hard to learn, basically. You have to impose them from the outside, and you have to be keeping track of them, but you don't have a way to get them out of the experience of interacting with the system without having a lot of hard work of coding them into the system manually. So roughly around the time that the previous work was finishing, some colleagues of mine decided to think of things in a very radical way. And using what seemed to me a very radical way, although for most of you it's kind of a run-of-the-mill, which I'll say, hey, we can use these newfangled, very efficient ways of training neural networks to do things like this. If I want to do inference, the premise is Bob is in the room, he cannot sleep. Can you conclude that Bob is awake versus in the room because of thunder and lightning, et cetera, can I conclude that it's sunny outside? Probably not, in fact, unlikely. But instead of trying to come up with a logical representation of the premise and the hypothesis like I was taught I should do when I was a graduate student, instead, they're going to say, can I produce some alignments between these terms that I can learn from data? And so they came up with this idea that you basically take your premise. In this case, in the park, Alice plays a flute solo, and the thing you want to decide whether it follows or not, someone's playing music outside, is that probably that sounds reasonable. So what you do is you learn these models that can align terms between these, very much like translation models. So you translation, and then you accumulate evidence. You say, well, these things, these pairwise alignments, this sum's a good one, so I accumulate all this evidence and then aggregate it all, and I decide whether the hypothesis falls from the premise or not. And this worked remarkably well for the time, with an extremely simplistic view of what it is to do inference. And part of it is because it could learn things like playing music and flute music and flute are associated strongly. It doesn't know that music is flute or the flute is, it just doesn't know any kind of subtle relationship between them, but knows enough about the alignments to be able to do this kind of work. And that is basically, and that led several others, including people here, to start saying, hey, we can do much more of that. So in particular, colleagues of mine at Google developed this idea of, basically went to an old idea from language modeling, where you say, well, if I can find a representation of text where it is possible to mask away a word or part of the text and predict it from the outside without, if I can essentially have all this multitude of Mad Libs and that I create a bunch of random Mad Libs and use that to train a predictive model. That model will have to know something about context. We'll have to know that this word fits well in this place and not in that place. And so you might know that break is the thing that should occur that. And so these techniques and related ones, which is basically first with the linguist from the 30s who said, know each word by the company it keeps, right? This is the way of doing it in 2018. And building these models, then these representations can be used in many, many other ways. Can take a representation be like this and then use it as input to some task you are interested in. So for instance, a question answering task. For instance, you have a question and a paragraph, and you want to classify whether a passage with certain start and end is the answer to your question. And I won't enumerate the multitude of results people have had along these lines. Everybody does this nowadays. So it would be kind of presumptuous for me to try to explain it in more detail, because I want to get this to some things related. So, so for instance, in this case, just give an example of how far is Jacksonville from Miami, and you can take big paragraph, and you find alignments between Jacksonville and Miami. So, and then identify a passage that fits in far, that associates with far in the appropriate way. So these kinds of correspondences, is what you think is happening in doing question answering with these models. But actually, the reason I picked it out is that what I just went through is a cheat. This doesn't happen in the model. Now, I'm looking at this and say, oh, okay, it found Jacksonville, it found Miami, it found something that feels like distance, and far relates to distance. I got the right result. But in fact, the model is not doing it that way. It's doing it in some complex, opaque way, and that is actually a question for concern. Because very much the example I gave earlier, with the Harry Potter question, you had a question, you have an answer, but then the passage that you select that you supposedly got the answer from does not tell you anything, actually the information that would support your answer. And this is what I'm going to talk about for a while now. And I'm going to do it through examples, lots of examples, enough to fit the rest. So here's a query. Who was the first person to see the Earth from space? Here's the result you get from Google. So you might say, if you know your history, some of us older, some of us who were alive when this happened, will sort of remember. And you might say, yeah, sure. However, I mean, there are few things going on here that are a little bit worrisome. Is outer space the same as space? We actually didn't go very far from the Earth, just above the atmosphere. But here's another one. Was there a window on the Vostok? The answer is yes, but it doesn't say there. And the final one is, could he look out and see the Earth? If I remember correctly, the pictures from, he was strapped to this thing, right? And could he actually even turn his head to see the? So now it turns out there is an autobiography of his that's been translated to English. And in there, he talks about seeing the Earth from space and all the emotions that brings. But it's certainly not in that passage. So this is kind of, again, should unsettle us, right? We get the right results for somewhat pretend results. And this is, so is this belief justified? That's the challenge that I want to give you to the younger generation here is this something that you want to live with for the rest of your life? I'm probably closer to retirement than most people here. Whenever that happens. And I feel a little bit nervous about leaving the world in this state. So here's another example. So this is a very different task. The task of, you have a record about some guy. It was some kind of mobster, as it turns out. In fact, you see this little text, FBI surveillance photo. This is the alt text for some photo. And the system, a summarization system, a sort of a text generation system from structured records that my colleagues were working as a baseline on, produces that answer. Franklino, blah, blah, is an American criminal defense attorney. Where does it come from? Well, FBI, right? It must be something to do with it. I mean, what else could it be? But now, what my colleagues did, very clever people, is to say, well, I'm actually trying to measure, come up with some notion of confidence of whether a particular word produced in the output is being supported by the input. And the details have to do with these models like the ones that I use for show the question alignment, question answering before, and also the BERT models use this notion of attention, which for those of you who haven't come across this notion, which is nothing to do with human attention, is simply the ability to have a model that looks at with different intensities at different parts of the input, just roughly speaking. And using those scores plus in some normalization, they say, well, if I'm not really convinced that this has support in the input, I'm not going to say it. So it produces this thing that is factually truthful and grammatical. Frank Lino, blah, 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 is an American. Now, if he was born in Brooklyn, what else could he be? It's sort of not necessarily a very good, it's sound in the sense, unlike the previous one, but it is a little bit kind of stilted. It's still. So here's a bunch of other examples. So some other colleagues of mine work on image captioning. It's actually, this project is very cool because one of the things they've done with it is produce a feature in Chrome that allows people with the visual impairments to get descriptions of images in websites that they don't have alt text. So you can ask for this image to be described to you and it to produce a description. And the descriptions tend to be pretty good. So here's an example. And they were comparing two different models. This is new work that's not published yet. They're comparing two new models. And I will call them just cautious and eager. I won't go into the details. Basically, is the amount of basically how much the model is trained to really be accurate, produce the training data. And here's a caption from the cautious model. It's kind of not useful, right? Close up of a person's hands. This is probably nothing about the money. So you can do that. A person counting money in his hand. This is great, right? You say, haha, we're getting somewhere. And basically, this model is trying to has a much more detailed view of what's going on. But the same model, sometimes, so we look at the scene. It's kind of a very nice scene, but also a very rare thing. How many of you actually being close to an object like that, the red object like that? Very few, right? It is not, those things don't run on the streets around here. A city in the snow. Maybe, it's actually a village, not a city, but never mind. It's a place, it's in Yorkshire, as it turns out. How do I know? I went and looked at the name of the pub and searched for it. It's in the hills of Yorkshire. But so, you're trying really hard. And, what is that thing? I don't know, but it looks like a locomotive of some kind. Like, it has kind of wheelie things that, and it's pulling something, This is the best it could make up. And this is actually points to a very important problem in these systems, is that because they have limited experience in their training data, when they are really forced to come to an answer, they make stuff up. And, well, we all do maybe. Although we shouldn't do that to the FBI, right? So here's a final example from this, because it's one that I really, that I think illustrates. So the cautious thing, Olympic athlete poses with a trophy. It's not bad, but it's like, what is the trophy? Aha! Great. Sorry. So this is a beautiful case, right? Because, probably gold medals are more salient in your corpus. People talk more, if you think about, this is trained by, how are these models trained? You get a lot of images from the web that have alt text, that have image captions, either alt text or have actual captions beneath them and so on. Use those as training data. How many, now go and think of how many images of people with a bronze medal appear versus with a gold medal. And you see why it would, and kind of the thing that, and also from the point of view of the visual features that I use in these models, it's not too far from gold, right? Anybody could make this point. We could make this mistake, right? It's not that bad a mistake, but it raises a really important point, which is if I was asked to I cannot go and ask this model, as I could ask any of you, hey, why do you say it's a gold medal? And you probably, unless you were trying to bluff me, you say, well, actually, I don't know it's a gold medal or not. It looks like gold to me, but I'm not sure, right? And it's certainly not a silver medal. I know that. But it could be, unless the illumination is really weird, but it could be a gold medal or a bronze medal. But that's justification. And this is a point I want to come back to. Justification is not something that these systems are able to do for themselves. So all of these considerations led some of us to try to say, what can we do to try to push the field a little bit forward in this area? So last year, some of my colleagues released a data set, a question-answering data set called Natural Questions. This data set was created from actual question-answer pairs from Google search, carefully curated to remove personally identified information and any kind of materials that could be offensive or controversial, and just make a set that could be used for research. It's a very hard question-answering data set. I don't know what those of you who work on question-answering think, but it's not an easy one to get really good. People are making progress on it, but it's still very hard. And what then? As we discussed the data set, and actually the challenge, the fact that once we released it, it took quite a while for anybody to actually try to present the results to it in the leaderboard, because it's so challenging and large and so on. We also started thinking ourselves, looking at our internal experiments, why is this thing hard? Why is this problem? And started looking at what is a good, how do you come up with the idea of what a good answer to a question is? So, in something like this, say the question, how many seats in the University of Michigan Stadium, you might say its official capacity is something. So that might be the number of seats. Actually, we don't even know its number of seats. It could be that there are a bunch of standing capacity. Who knows? I don't know that. But it's not so bad. Many people would provide. That's not an unreasonable thing. You have to also figure out that the University of Michigan Stadium, even though there's Michigan Stadium here, et cetera, it's nothing that explicitly says the capacity belongs to that. It's only implicitly to the pronoun it's there. It's the possessive pronoun its capacity. You need to connect that. If you want to explain why you produce that answer, you need to do that connection. So what it says there is inference from y is official capacity is y to y is the right answer to how many seats in X. And finally, we need to actually do that. So we need to do that connection. And if we have all these elements, then we are tracking the evidence that led us to this question in more detail, which our current question answering deep models are not doing directly. Here's another example. Where did the captain sleep in the Mayflower? So is the text. First of all, here's a few complicated things. The captain, there's this thing that you have to figure out, that the captain is the person, is Master Christopher Jones. You know, knowing that the Master Christopher Jones, the captain, is not a direct inference. You know, we know that, you know, some of us know that master was the title used for captains in English ships during some period of time. And the aft on the main deck in the stern was a cabin. Why is it that where he sleeps? Where did he sleep? You know, there's another inference, which is, and this goes to common sense reasoning, and this is, you know, I look in the engine there, and if you look at this one, I say, I want that one. So here's the good news. If we get this right, we'll be releasing another data set. and then that you can all go do your explorations on. So what the point I think I want to get to here is, we need to find ways of, and not just because we'll get better answers, more accurate answers, ultimately, but because we'll get better trust from our users. Why is it that we're saying that such and such is an answer to your question? And when any of us is challenged in a conversation to justify something we said or something we did, we might bluff at the start, but if your questioner is persistent, we might have to actually dig in and say, oh, because of this, because of that, and there might be a debate. And the first step to that is to identify those key basic elements, even a simple question answering task like this, those key elements that support the inference that you make. And so, I mean, this whole line of reasoning actually got me back to think about some line of work that Ben was involved with two of his former students, João Graça and Kuzman Ganchev, on machine translation. Why machine translation? I'll first make the point that machine translation is a domain where this same set of problems occurs, right? Because in machine translation, one of the big challenges in modern machine translation, and the Google Translate team reports up to me, so I'm very familiar with this problem, is that it's very hard to make sure that the translated text is faithful to the source text. It requires huge amounts of engineering and data selection and luck, to be honest, to achieve reasonable translations, especially when the input is more unusual. I mean, there's an ongoing joke with Google Translate. I'm sure that other online machine translation systems, where people supply an input which is completely nonsense in language X, especially and try to translate to some other language Y, typically a language Y that does not have a lot of text on the web. And what happens is you supply nonsense X in language X, and you get a verse of the Bible as a result for Y, because that's what typical training data that you have is because you have all these translations of the Bible, right? So that's kind of embarrassing, right? And it's embarrassing, but if you think about the embarrassment carefully, what you know is this system has no way of accounting for its actions. Right? It does not have the way to say, hey, I'm going to produce this word or phrase here. I better know where it comes from. I better have some reason to decide that this is a good thing to say. Oh, but this input makes no sense. It's completely gobbledygook. So if that's the case, a human translator, even a relatively incompetent one, will say, well, I have no idea what that means. So maybe I'm just going to do a literal translation, or not, or give up. And I have experience of this because when I was a kid in college, I made some money translating from English to Portuguese, probably very badly. And so I remember reading things, and it wasn't gobbledygook, but I didn't understand it. And I was just like, oh, maybe I just do a literal translation, and that will be okay. At least it won't offend people too much. So that notion of support and justification is something that Ben and his students did. So what they did is this really interesting thing, and let me make another point here. So the symbolic models I talked about before have this nice property of being able to account for everything, but are extremely fragile. The new models are much more robust in the sense that it can handle less expected input and then can do associations and correspondences that are much more indirect. But they can be, they can hallucinate stuff or miss stuff very badly. The ideal world is to be one where you have both a notion of, this fuzziness that you have in neural models, this ability to be a little bit approximate and a little bit do correspondences that are somewhat indirect and learn them from data. But at the other side, you also have to be able to explain your work, to show your work. Like, they're academics here. They know that this thing they say to freshmen, show your work. It's maybe you don't say that any longer, but it's a useful thing. But the problem of showing your work is that it requires you to, it forces, if you think about that too strictly, it forces your system into a mold where, again, it goes back into the symbolic framework where you have to, you basically are working these symbols discrete symbols that have very little give in them. So a different way of showing your work is saying, look, you do the thing, whichever way you care about, but then let's impose some constraints, some sanity checks to make sure that, for instance, in general, for instance, in translation, on average, each input word produces one output word. If I say from going to French to English, on average, maybe it is not one, it's 1.2 or something. But the point is, on average, it's very unlikely for a word to produce, for the majority of words in the input sentence to produce 5 words in the output. And you just have to pay attention to that. If you have that constraint, then you're unlikely to make up stuff. Because to make up stuff, you have to produce words on the output for which you don't have any support on the input. Now, you could throw away stuff from the input, but then you can do the same thing in the other direction. Every input word should have a correspondence to the output words. So that idea is the kind of the basis of this extremely nice work that I think that people doing neural networks today should revisit, which is the idea that you do your optimization under external constraints that force certain marginal statistics on the process. Let's say there has to be a rough correspondence between the length of the input and the length of the output in a question. Or in a question answering setting, that anything you produce on the output should have, some support in the input. You might not know exactly where it is, but at least you have to have some strong support on the input side. And what is so innovative about this work still, and which I think is underappreciated in the work people do today, is that it's not based on the idea that I have to constrain the internal mechanism of the system of say, question answering or of the system of translation, but rather what I constrain is how I train it. How I force it to, and in particular, how I can produce these additional constraints on the optimization, the optimizations mechanism that I use for training a model, that requires that on average these constraints are met. I think this kind of idea is really ripe for return to our work today, and it gives us a first little step towards, having justified inferences, not just inferences that seem okay from the data, but where you actually are free to make up stuff or forget stuff just according to whatever your training data said. Some of you that have been talking to me last couple of days kind of suffered from the fact that I tend to get very fond of particular books and keep pushing them on people. There's a book that I really recommend. It's called The Enigma of Reason. It's by Hugues Mercier and then Sperber. So these are evolutionary psychologists. And this book has really inspired both a lot of what I'm saying and also my thinking about these problems, because it's about separating what we think people are doing when they are reasoning and from what they actually do. And in particular, think of reasoning and justifications as being basically a social phenomenon, something where you are challenged on your conclusion or your action, and someone else is going to say, why did you do that? And I say, well, because blah, blah, blah. And they'll say, no, but that doesn't make any sense. Here's the reasons. And you can iterate that, and eventually maybe you come to an agreement. Maybe you discover that your conclusion was wrong, and you change your mind. But basically, you have that reasoning is about external criticism. It is a very fundamental piece of our ability to reach better conclusions, is that we can criticize each other's conclusions. And what I see in a sort of computational way, this kind of work that of Ben's going towards is exactly the notion that you can have this sort of external critics to an inference process, to a learning process, that can constrain it to be more responsible for its conclusions than the things we're doing today. Thank you.
We can open the floor to some questions if there are any.
So I really loved a lot of examples that you had where we can really think about the reasoning versus associative pattern matching. And even for cases like the capacity of the stadium example, I can totally imagine a machine today can answer it correctly based on just getting lucky, because that's the only number that actually makes sense in the paragraph. And there are a lot of mentions of Michigan in the same paragraph, so it actually does not need to do CoreRef. And which makes me think that in a way, currently available benchmarks are all encouraging the models to do exactly finding the shortcuts and never mind actual reasoning or even learning something about the world, both encyclopedic knowledge that was part of that example, but also common sense knowledge, like you typically sleep in the cabin as opposed to steering room, if those are the only two rooms mentioned in the paragraph. And so how do we even set the data sets so that we actually encourage correct learning?
So if I want, look, I don't have any general prescription here. I think that what we're doing with the data that I showed a little bit towards the end, and this is very preliminary, and I'm not claiming that this is going to work. So let's see if I can show this example still. So in this example, it's actually, and there are many others like this where our current systems get this wrong. You know, where you can trace the evidence, but we actually don't get the right, it produce wrong answers. So in natural questions, there are many, many failures where I can look at this type of analysis and see, oh, we matched the question term to the wrong thing in the answer and so on, in the passage and so on. So at least I'm hoping, you know, if we get this right, that in a little while, you'll have a data set like this, annotated, that you can do a little bit more experiment. It's small. I mean, it's not going to be gigantic because it requires a lot of human annotation. But it at least gives a methodology. So there's actually a paper in submission now around this. We'll see where it goes. Where it gives you at least something that people could imagine. For instance, try to crowdsource more of these kinds of things. You know, where you try to get, you know, some explanation. And by the way, these annotations, I think, is not the ones that are, at least not in the way we're doing them now, is something that I don't think I can crowdsource. I think I need linguists to do them. But ultimately, we might find a simpler way that could be crowdsourced. So that's one example. Turns out that roughly, of all natural questions, which is several hundred thousand examples in the training data, or 300 or something like that, right? There is like 70% roughly have a pattern like this. It is, if you can find the referential matches, you can get your, in the few other things, you can get your answer. So that's so it's a limited scope, but I think it's a first step. And it's also it's a limited scope because it's a one-step thing, right? There are no deep cascaded inferences. So that's all I say. We try to create, the challenges we face in practice lead us to come up with ideas for things we could do more on the research side, but I don't have a general prescription, unfortunately. I'm in the business of kind of being practical here, which is, here's what I can do now. And by the way, just kind of a comment, getting this type of annotated data sets is super expensive, right? And one of the things that I try to convince my colleagues and my people that come up with the big budgets at where I work is, hey, this is an important thing for us to do for the community, and I'll continue to do it for as much as I can. But it's it's not going to answer all the questions you have.
Thank you.
Thanks a lot. Really interesting talk. I was wondering, with this idea of explainability, it kind of seems like there's maybe two ways to think about it. One is with your college freshman example, kind of explaining the steps that the algorithm is going through in order to produce an output. But then there's also this kind of coming up with an excuse after the fact for this is why I have, done this particular thing. And I'm wondering if you see room for kind of doing that first kind of introspection as well as just kind of producing an excuse after the fact.
A super cool question. You just, I think you nailed the kind of the challenge we face here, right? Now, I think it really depends on the type of problem. So for calculus questions, right? Clearly given the way we teach calculus, right? The average freshman in calculus will be going through some kind of a recipe in their minds, applying some known equalities and so on. Integration by parts, whatever it is, right? And so it makes sense because really it's you are trying to teach a human to go through a sort of fairly formal procedure. Now, just as a footnote and an aside, if you talk to any working mathematician, or even more so any working theoretical physicist, they don't do any of that. They will come to I remember working with physicists a number of years ago, and they'll come with some derivation, and I'll say, wait a minute, but how does that fall from that? It's oh, no, there's some second-order terms you can throw away. And I'm like, how do you know that? And then anyway, so even in that case, it's only because a student is a very a calculus student, or an introductory algorithm student who trying to compute some big O, is going through a very prescribed, very formal recipe. That's why how we teach those subjects. They will they can show their work. Whereas if you took a serious practitioner, whether he is a mathematician or think about talking to your doctor about some complicated situation where they are recommending a particular treatment, and you say, why, and what are the alternatives? you see that there's a lot of jumps that people take there, and it's a question of sort of trust, whether you trust that some of these are justified or not. Now, then the second way you framed it is, oh, the other stuff is after the fact, bluff, right? But it is not, right? Very often, if you ask me, why did you buy that car? I don't like the color. And I can tell you, oh, because my old car was falling down, it was falling apart. I would have to spend several $1,000s to fix the engine. And then they decided it made more sense to buy a new car, but they didn't have any available except that color that I don't like either. But now I'm used to it. This is actually the true story, right? But so I gave you the justification. You nodded. It doesn't seem to be a sort of like completely made up one, and it isn't, right? But it's like, if you think about what happened at the time, I was in a hurry. I needed this car. I didn't want to be bothered with waiting for one or looking for another dealer. I just wanted to get done with it. Buying a car is such an annoying thing anyway, right? There are all these subjective and emotional parts of it. Like, I just hate shopping for a car. And so all of those factors are not my justification, but they were important in making my justification. It also is another Subaru, right? Why do I buy another Subaru even though the previous one was falling apart? Well, because I like the way they drive, whatever, and maybe because I don't want to change, because it's kind of annoying to change and learn new things. So all of those factors that go into a complex decision are not in your justification, right? It's not like mathematics, and yet they are still useful in this conversation.
So why not train machines on arguments instead of one-shot question-answer tests?
Because, unfortunately, you don't collecting well-constructed arguments is not something that they are not. Look. They're not naturally occurring in quantity.
On mechanical terms, I ask you to ask me why, and then I ask me to justify.
So now you get into a question which is really, I think, really interesting, which is about whether these things are ecologically sound or not. So when I look at question answering, right, that is an actual query that someone posed to Google, and this passage is an actual answer that is provided. Now, I know that someone wanted that information, and I think they were satisfied with the information because we have ways of guessing as to whether, for instance, the person did not reformulate the question afterwards 3 times. Right? We knew that they stopped there. Okay, done. They're now asking something else about the Mayflower or about the Pilgrims or whatever. And they liked it. They got it. So we can infer that and say, hey, that was right. So we have a naturally occurring, for some definition of natural, example of behavior that we can infer something from. Whereas in mechanical, if you get mechanical Turk, so we've done a lot of work, for instance, on dialogue with the not mechanical Turk, but internal equivalents of, and we found it's really hard, even when you're paying people quite a bit more than they are paid in mechanical Turk, to get them to stay on task because they actually don't have anything at stake except whatever they're going to be paid for. The person who's asked that question probably has homework to do. If we did not give them the answer, they would have an answer that was satisfying for their homework. They would be unhappy, and they would try again, and they would do other queries. And so the behavior is more natural, more motivated. The person has something at stake in this interaction. And this is, I think, a problem that we as a field have to face, is that for many of the users of crowdsourcing, we have not come up with the mechanism designs, with the sort of that put the right kinds of things at stake in the interaction to produce a naturalistic output that our systems can learn from.
So as corollary to that, and I'll finish with that, what about requesting a trust metric from the user after the fact, which both puts into question what do you trust this or not, which is socially brings the awareness to the fact that there's an algorithm at play here and potentially not to be trusted, but also allows you to use reinforcement learning after the fact.
So this question of asking feedback from users is one that keeps coming up. I mean, the conventional wisdom at Google, and I don't know whether I totally believe it, but as well as I've heard all along, is people they never do it. They will not respond or not. It's too much work. They either get to what they want or they don't and move on, and they are not going to bother to click on did I trust this or not. This is conventional wisdom. I'm not sure that this is right, and I think this is something we should experiment with every few years to try to see whether there's better ways of eliciting some kind of feedback. And so I'm just saying, I'm in this case, because in the end I'm not involved in launching products, right? So except with Translate, where we actually, for instance, have been doing some things recently to deal with some questions of how you can deal with ambiguity better in translation, and trying to come up with some interface designs that allow users to select between alternatives and maybe to give feedback on those alternatives. But it's really, there's a sort of a fine line, especially when people are using phones as well, followed by big screens, between providing what the user is looking for and kind of overwhelming them with kind of cognitive load that is peripheral to the task they are doing. So anyway, I'm not saying no. I'm just saying the conventional wisdom from the people that design and do UXR at Google has been that is not a very productive way to go, because it also produces very biased results, because the people that provide feedback tend to be the ones that have very strong opinions, and sometimes kind of a very strong point of view, and that might not be representative of the value of that particular result to users. Anyway, I'm just, in a sense, I'm just reporting what I'm told in this case, not necessarily something I deeply believe. But one more.
One more.
Yes. Great. Hey, nice seeing you.
Hey, thanks for the nice talk. I have a question about the gold medal example. The gold medal example. Because I've been playing with BERT and similar models, and I keep noticing that if you ask it for substitutes of a mask token, where obviously the word should be of some specific semantic category, like colors or numbers, then you can see that it sort of like knows that it should be of that semantic category, but it doesn't always know the correct answer, and it often tends to predict the more frequent instances from the category, regardless of the context. So do you think, and I mean, it's sort of by design, the way these models are trained, they are supposed to generalize, but so do you have any idea on how to address that?
So I think they generalize, but generalize in ways that are towards what's likely given what they've seen, not to what is generally possible. It's the notion, for instance, he's looking for a color. This is an external observation of this is something that we from the outside are saying about its behavior, but in fact it's looking as something that is from this class of things it's observed, and some more than others. It's a soft class, and some of those are, and most of them might be, the top 20 might be colors, but if you look further, probably will be other things. I don't know how far down the sampling did you go. I could imagine that after a few colors, you start getting things that are totally not colors. And this is basically the challenge of all distribution models, not just BERT, but all the ones before. And you worked with them before, right? And Ido has worked with them for decades, and we did work together, and we had some great results, except that, when the top 10 are great, and then you start going down, and you start getting all this random stuff, which is not random, but it's not, the concept, in a sense, this concept that the system formed is not at all the concept that you have. And I think this is actually a deeper issue here, and I cannot characterize it technically, but I can sort of hand wave about, which is that the sort of the representations that the systems form, even the neural network ones, are very diffuse, are not sufficiently sharp, and and I was telling someone about this. So many years ago here at UW, Patricia Kuhl, a psycholinguist, child development expert, did these amazing experiments, which I never forgot, about child language acquisition. And the sort of the rough facts are that 3-month-old babies do not have a sort of very vague and broad discrimination of vowel sounds. 6-month-olds, any stimulus, vowel stimulus latches to those of their mother tongue. And by the way, 3-month chimpanzees behave like 3-month-old babies. 6-month-old chimpanzees continue to behave like 3-month-olds. So what you get is this beautiful modeling of these sort of attractors, these vowel center attractors. And in fact, for babies that are bilingual, because they have parents of, they're different native speakers of different languages, they will have the centers for both languages. So basically, they've formed a categorization of the vowel sounds into this small number of discrete elements. I don't think any of the models we've built today have a behavior like that. At least nobody has convinced me that they do. I mean, there will be really interesting more research to be done as to to try to understand the attractors. So if I give a stimulus that is off, do I get clamped to a particular point, or are all them spread out? Do you see that? This is something I think is part of the problem, is that there is no pressure in something like this to have something that is just a color, or just a number, or just a person. It's a pressure to have is stuff that that's person-y until it kind of, you look a bit further out, and then it's like, maybe not. There are no sharp cliffs at the edges of these concepts, and I think that's part of the reason why people still say, oh, we still need symbolic reasoning. They need, because these things are too washed out. Anyway, thank you.